I would like to remind you all to be signed in with your institute email address. Okay, so that's a must for this course because we can't admit people from outside this domain. Okay, so yeah, so it's a strange world now. We are having to do everything online. Otherwise, it would have been great to just meet everyone. But anyway, that's the time. And so let me just share with you. Some of you probably have seen this web page. So I'll just share my screen. Sorry. Okay, is my screen visible?
Yes, ma'am.
Okay, so yeah. Okay, so the course is, it's on theory and algorithms of optimization, and a very important prerequisite for this course is linear algebra and also calculus. Now, I'll be covering some aspects of this as a refresher in the next week, but if you are not very familiar, I urge you to brush up the basics of linear algebra and calculus. So you can use any standard textbook for this. And in this course, you're going to have some programming as well, actually a good amount of programming too. And it is a heavy math course. Okay, so the class timings are as what we have in the timetable. Okay, and there's no one textbook that I'll be following for this course because different books are good for different topics. So, but by and large, these are the three books. So one is this book by Leuenberger and Inoue. And then there's this book by Chong and Zach. So even for the basics to brush up linear algebra and calculus, you can refer to this Chong and Zach book. And also this book by Boyd and Vandenberg for the later part of the course. Okay, so I will be sharing this webpage with you all. Right, so these are going to be primarily the textbooks that will be useful for you guys. And also another very useful reference is this course on computing and optimization by Professor Amir Ali Ahmadi. So I'm just showing you the web page. It's actually this is by this course is for the students in not computer science. It's an OR department, an operations research department. So that's why they have a computing aspect to it. But for you guys, I mean, I think many of these aspects you probably would have learned in some other courses. So there'll be some things which I will follow this material closely on the optimization part. So this is a good reference material as well. You should go through some of these lectures as well. Okay. So, and the additional references are these books by Nosidal and Wright, Fletcher, and Bert Simmer's An Introduction to Linear Optimization. And this last book is mainly useful for the modeling aspects. Okay, so anyway, as and when I cover portions, I'll probably also give you pointers to which references you could look at. Okay. So now coming to the grading part, you'll be graded based on 4 assignments. Okay, an exam, 2 exams, midterm and final, and also on your class participation. So these are the weightages. Okay, so 25% for the assignments, and the midterm carries 30%, a final of 35%, and 10% for class participation. Okay, so all these assignments are to be done individually. Okay, you can of course discuss with your classmates, your friends, but what you turn in has to be done. It has to be an individual effort based on your own understanding. Okay, and for the exams, there is no collaboration. It has to be done on your own. No copying. It's not going to be permitted in any way. Okay, and if we suspect that people have copied, we'll also have a viva. Okay, so we're very strict about this aspect, right? So so these are some of the things. So all the lectures are online. So I really urge you guys to make it interactive. Stop me at any point of time, and it's very easy in an online class to the mics are off, the video is off. You can just go somewhere else, watch a movie or a game and all that. It's very easy to do that. But remember, you guys are in an IIT, so you know how many people get a chance to be here and do their best, and you really have a lot of potential if you attend the courses well. Okay, so it's in your best interest to, you know, understand from the course and take it further. Okay, so yeah, I would really urge you to make this class interactive. Okay, so uh, yeah, so the lecture plan is broadly in this form. So at this moment, maybe a lot of things wouldn't be clear to a lot of you, but it's a very rough plan. And, you know, as and when the course goes along, like this would have been the ideal case if everything was a physical classroom, but being online, I mean, there are some challenges and stuff. So we'll see as it goes. If in the best case we'll be able to cover all of this, but even, you know, if we're able to cover only a subset of this, it's fine. You know, as long as things are clear. And yeah, if we have more time, that is an ideal scenario. There are a lot more things to do in optimization. So either way, it's fine. So this is just a guideline of the topics. Okay. So any questions till now?
Ma'am,
Okay.
you mentioned research, I mean, operations research. So
Right.
could you actually mention how optimization comes there?
So yeah, operations research actually is a domain. It's more of an applied domain where you use some of these techniques, some of these modeling techniques to solve some problems. Okay, so it's more on the formulations themselves. So on building efficient formulations, but you know, an operations research person may or may not get into the optimization details. Okay, so there's a very thin line of difference between the two, but nevertheless, it's a basic subject for anybody doing an undergrad or a PhD or anything in OR as well. Okay, so that's why for this topic of optimization, of course, from the Department of Math, people usually deal with this, but it's done in a sort of different flavor. Okay, so an OR department usually does good justice to this topic. So hence, you know, that's the way. I mean, that's why this I would recommend as a good resource. Okay. So, yeah, I don't know if this answered your
Thank
question.
you, ma'am. Yes, ma'am.
Okay. Yeah,
Ma'am, will the recorded lectures be available on Google Classroom?
yeah, I'll upload it as and when I get it. Because I guess many of you have probably have issues with bandwidth and stuff. So I'm just
Yes,
recording
ma'am.
it so that, you know, for everyone. Yeah. Okay.
Thank you, ma'am.
Okay. So, so this class, I believe there are some third year students, fourth year students from the undergrad, and MTech first years, and I guess couple of PhDs. Okay, so yeah, it would be useful to get a background at some point. So I want to get a, you know, sense of like from the undergrad class. Are you familiar with things like polynomial time solvability, computational complexity? Have you done a course on this? So anybody can answer
I'm not a course, but we saw these topics last sem in logic.
in
Third
logic. Okay. So that was a core course. That's all of you had done it. Uh,
yes, ma'am. I believe fourth years have that as well.
Okay, good. So I guess, yeah, so you guys should be familiar with that. So that's also an important part of optimization. So that's what I wanted to know. Okay. So I guess with these things being said, maybe I can, you know, start off by giving you an introduction. Right. Okay. So yeah. Okay. So the screen is visible, right? Just to confirm.
Yes, ma'am.
Okay. So yeah, so what is optimization, right? All of you have done optimization at some point and probably are doing it every day, okay? Without your knowledge, of course. So one example here is when you're planning a trip, okay? You're visiting some place, say Berlin, for a week, and you want to visit all the important places there. Okay. Now, how would you schedule this? So the important criteria here are you want to minimize the cost of moving around. You want to stay in some place. You want to choose a place to stay such that the cost of moving around is low. And you also want to maximize the number of places covered. So these kind of things you all would have done at some point, right? Some vacations or anything of that sort. Another example is for sure you would have done this. Which university should I choose for BTech, Masters, or PhD? So should I get into an IIT? Should I get into an NIT with a different branch, and so on and so forth? So yeah, you will look at different factors, right? About the ranking, then opportunities that you get later on, then maybe for some of you, maybe even the fees is an important thing. And nowadays, the risk of travel from hometown because of COVID and other things, you want that to be minimized. Okay, so I mean, this is just an illustrative list of what factors you might consider, but it could be different depending on each of you. Okay, so I mean, these are also optimization problems that you would have done. And also preparing for exams, you're possibly crediting a lot of courses and your exams approach, so you want to plan your time so that you give enough time for all the subjects, and towards the end of the sem you have a lot of assignments which are pending probably, and you want to do that well, and you still want to have enough time to enjoy, you want to relax also. Okay, so yeah, so this is also an optimization problem. So so you get a sense of it, right? Like everything you do in your daily life, that those are also optimization problems. Okay, so unknowingly you're solving optimization problems. So why all this fuss about optimization? What is the big deal? Okay, now what you are going to do in this course is going to be something about how these problems arise in engineering. So what you had for these other problems, and you had some intuition on how to solve these, right? Like even without thinking, because you understand the problem well, and so you have an idea how to solve it. But in actual problems that arise in engineering, in computer science, and everywhere, you many times don't have much of an intuition before, and you have the problem given to you. So in that case, how do you model them? How do you solve these problems? Okay, and in this course you'll also use the software like MATLAB or Python to solve these problems. So I would leave it to you guys. I mean, like this we can chat about it when we announce the assignments. But yeah, the programming language, it's up to you. I mean, you can use a language of whichever you're comfortable with. But I mean, this is an important part of optimization, like using some solvers or like coding the algorithms yourselves. Okay. Now, so much of the course will focus on the first four aspects. Now, in the last 2 points, what I've mentioned is some optimization problems are easy in the sense some of them are polynomial time solvable and some are hard. Okay, so an important part of optimization is to recognize these. You know, so if a problem, why do you know why do you want to know it's hard? So if it is hard, you don't want to spend all your energies into solving it, right? You probably want to get some kind of heuristics or approximations. And if you can recognize that the problem is easy or polynomial time solvable, then you get into the actual solutions. Okay, so these two, the last two, are also some things that would ideally be good to have. But yeah, if time permits, I would focus in that direction as well. But primarily, we'll try to focus on the first four aspects. Okay, so now about the problems that arise in engineering. I mentioned that in engineering there are these problems which naturally come in. So to see that, here are some examples. So in machine learning, for instance, consider recommendation engines. Okay, so many of you, I mean, I think all of you would have bought something at Amazon or Flipkart at some point of time. And whenever you buy something, like you also get recommendations on what other things you can buy. Okay, so what Amazon is trying to do is it's trying to get some revenue from these recommendations. So it recommends something good, then probably you will buy something, right? So that's why it's critical that these recommendations are, really good. Okay, so what is happening in the back end is an optimization algorithm. It eventually boils down to that. Okay, and it's also important for the optimization problem to be solved fast. Okay, because there's just, you probably will be on that page for maybe 2-3 seconds, and in that time the recommendations have to be generated. Okay, so so these are the kind of challenges. So optimization is there in machine learning. Now, in the case of marketing, so like social networks are now there everywhere, right? So like if you have a network at your disposal, and suppose you're the CEO of a company, and you have a new product that is released, and you want to tell everything about this product to a few people who can in turn spread this info in this network. Okay, so now what you want to do is you have some budget as a CEO. You want to budget everything well, and based on this you decided on some number K. So maybe some 100 people in the community, you want to tell them about the product, and in turn you expect them to spread this information. So who are the people you should choose for this? That is also an optimization problem. Okay, and where the objective you want to maximize is the number of people who get the information. Okay. Now another example I wanted to highlight is on these app-based services, for cabs. So I guess it's not there in Goa, but in every other place perhaps, like Uber and Ola and all that. So where you want to match drivers and routes to trips. Okay, so when somebody makes a booking for a cab, you want to assign a driver to that booking, and the driver should be near the person who booked at that time. And every trip has to be matched, because you can't have a disappointed customer, and you also want to pick a route which is as short as possible. Okay, so here there are multiple optimization problems that are coming in. Okay, so these are all like big systems, right? And the basic thing for all of them is an optimization problem, and that's why it's very important to learn this. So any questions so far?
Ma'am, actually, I had a question.
Yes.
Why do we call them optimization problems when they could be constructed as constraint satisfaction problems?
Yeah.
Or is
So
there a difference?
so constraint satisfaction is like you don't have some objective which you're trying to maximize, right? So for example, in this marketing example, you want to maximize something. There's some metric you want to maximize subject to some constraints. So in addition to satisfying some constraints, you also want some metric to be optimized. Okay, so that's why it's an optimization problem. And similarly for all these things, right? These app-based cab services, you want so like here a possible metric would be the distance of the driver to the source. Okay, that has to be minimized. Okay, so yeah, or no trip is unmatched. So the number of or minimize the number of unmatched trips or something of that sort. Okay, so that's why these come in as optimization rather than constraint satisfaction. Okay, is that clear?
Thank you, ma'am. Yes, ma'am.
Okay. Okay. Any other questions? Okay. Okay. So now let's do an activity. Okay. So I'm going to show you some graph like this. It's a network. Okay. So is this visible? Is the graph visible?
Yes, ma'am.
Yes, ma'am.
Okay. So this is a network, and say you're trying to send some oil from this node S to this node marked T. Okay. So this is an example taken again from Ahmadi's course. So here, what these numbers are is these are all links. Okay, these are various points of the network, and there's this channel which is going from S to A. There is a link, and there's a link from A to B, and so on. So each of these links has a maximum capacity. Okay, so you want to send some units of a product, maybe some oil. Okay, and these links give you the, these numbers give you the capacity constraints of each of these links. Okay, so you want to send oil from S to T, and it should be such that whatever comes in at any of these middle nodes, right, A, B, C, all these nodes other than S and T, whatever comes in should be same as whatever goes out. Okay, so suppose you are going to send, so let's just take this node A. So 10 units, suppose you send here. So outgoing is just 4, 5, 6, 7, 8. So this is not feasible. Okay, so at max you can send only 8 here on this link. So okay, so those are the constraints of the game. Okay, now with this, what you need to do is you want to send the maximum amount of oil from S to T. Okay, so is the question clear?
Yes, ma'am.
Okay, so can any of you just make an attempt? What could be an amount of flow that you can send? So this is actually called a flow. It's a max flow problem. So can you make an attempt on how much can you send from S to T? So I'm just connecting my tablet so that I can write on this. Okay, so yeah, do any of you have some ideas on how this can be solved?
Ma'am, it would be 21 because 21 units can come out of the source max.
So an attempt one is 21. Okay, can you tell me how you sent 21?
Ma'am, actually 21 would come out of the source, but I think 11 would be able to reach the. So max flow would be 11 in my guess.
11. So can you tell me how you got 11?
So B, G, E, D all have outward nodes that go out with two. So like I just calculated how many the total was. So 3, 2, 2, 2, and 2.
Can you say again? Like, can you tell
So
me how much flow you calculated on each of these
11.
nodes?
So on each, so
Each
B
of
would have
them.
outward 3, G would have outward 4, E would have outward 2, D would have outward 2.
Okay, tell a little slowly so that I can just mark it on this graph.
So,
So what would be the flow on SA?
ma'am, I did not calculate it for the entire network. I calculated it at like the crucial point where I know that beyond this, the flow can't be greater than a certain value.
Okay, so that was at which point?
So the B to H, G to H, G to F.
Okay, along this part, right?
Yes, ma'am, the cut there, right?
Okay. Okay, so I think you already knew what a cut was, I guess, right? So who is this? Is Devyani, is it?
Yes, ma'am.
Okay, fine. So yeah, so this is a very, I think you're already familiar with max flow and then cut kind of algorithms, I suppose, right?
Yes, ma'am.
Okay, so is there anybody who doesn't know the max flow and min cut algorithms?
Yes, ma'am. I don't know them.
Okay, so yeah, so why don't you, did you understand what she said?
No, ma'am.
Okay, so why don't you give me an attempt? So thanks, Devyani. So that's a good attempt, but I guess there are many of you who still are not familiar with max flow and min cut kind of algorithm. So give me an attempt, right, on how to go about from S to T. Need not be the maximum. Give me some attempt.
Okay, ma'am. Just some attempt.
Can you speak a little louder? I think I'm not able to hear you.
Okay, am I audible now? Hello?
Just a second.
Am I
Uh,
audible?
I think it's still faint for me somehow.
You're audible, but you can also try to increase the mic volume.
Okay, I'll do that. Yeah, maybe someone else can give an attempt till then. I actually don't know how to increase the volume. So.
Yeah. So would anybody else want to try?
Sure, ma'am, I can try.
Yeah.
Like, ma'am, I actually got the same answer as 11, but
Okay.
what I did was that I first just observed the graph and I just listed the links that was giving an inflow to T, that is the H, F, and I. These are the nodes which have an inflow to T.
So
So
inflow to B, is
T,
it?
T for tiger.
Okay. To T. Okay. Sure.
Yeah. So H, F, and I have an inflow to T. Now these inflows are a lot bigger than the, I will say, most of the inflow to other nodes. Like most of them have an average of 2 or 4 or something like that. It's
Okay.
a bit low. So these values, that is 6, 9, and 7, will always be greater than the value that these nodes, that is H, F, and I, can get. I just assume that, and then I
So
tried
that's
to send the maximum to these nodes.
okay.
So for that, the limitation came again at like the J node. Like the J node only has an inflow of 2, and it can give 1 and 5 to F and I.
Mm-hmm. Okay.
So,
So
but
these
it
ones, right?
won't.
1 and 5.
Yeah, but this won't be possible. Like the 5 won't be possible because the J has only an inflow of 2. So again, the outflow of J to I will decrease to N.
Okay. So broadly, the approach you constructed was like you were backtracking from T, and
Yeah.
and then you were trying to like greedily solve. Like at T, you were trying to see which nodes were critical and which edges could carry the maximum, and then you were trying to backtrack from there, right?
Yes, sir.
Right. Okay. So yeah, that's also a fair enough approach. The thing with all these is okay. So this approach, like you never know when you're done, right? Like, yeah. How are you sure that this will always give you the optimal? So here, so the answer here is indeed 11. That's right. Okay. But you also need to have a way to identify that this cannot be greater than 11, right? 11 is really the best you can do. Okay, so yeah, these are all like really good attempts. So what Devyani said, that is actually a way you also verify that you cannot do better than 11. Okay, so for most of us, how we would solve an optimization problem, if you some of you already have a background, so it helps. But if you at first you just see an optimization problem, then what you do is you will start by constructing some solution. Okay, so perhaps something of this form. Okay, so this is something that just as a layman, you just start making some flow. So here I'm sending 3 here. Okay, so these are all, this well within the capacity, another 3, and so I'm looking at it as paths. Okay, so this is another way of solving it. So you look at this path. So here you can send a maximum of 3. Okay, now you again look at another path in the network, and here you can send 2. Okay, and now so in that way you can go on, and this will give you only 9 units. So then you try to improve it in some way. So this is another way you can solve optimization problems. So in general there are different ways, but you also need to be able to find when to stop or when you have reached the optimum. And for that, what Devyani said was is one of the ways. Okay, so where in these kind of graphs, if you cut the graph somewhere, okay, so if you cut, oops, sorry, it's just, okay, it's for some reason using the eraser. So let me just try to show it in this graph itself. So if you cut the graph, there are different ways of cutting it, right? So if you cut the graph in this manner, then everything that is flowing out. So what's the maximum that can flow out from here? Okay, so this is 9, then you have 2, 2, 2. Okay, so Devyani, can you just tell me which is the cut you looked at versus the cut?
Ma'am, B to H, G to H, and G to F, E to
B
F,
to
E to.
H, sorry. Okay, so ignore this thing. For some reason, I'm not able to. Okay, yeah, good. So tell me again, B to H.
G to H, G to
Okay,
F,
G
so,
to
and
F.
that cut down to D to J. E to F and then D to J.
E to F, this one, right?
Yeah.
Okay, so this is the cut. So you were quite fast at doing this. Okay, so if you look at this cut, so if you're going to send anything from S to T, then if you construct some cut here, the maximum that you send cannot exceed the value of this cut. So these are the edges which are cutting, right? So this has a capacity 3, then here there's a cut of, a value 2, and this is constrained by the capacity 2, and between E and F there's a constraint of 2, and again between D, J there is a constraint of 2. So this value is 11, and how much you send is going to be constrained by this cut. So you can compute any other cut in the graph also, and that's also going to be an upper bound. So Devyani, one thing you had to tell me was, how did you know that this is the cut? So if this is the case, then you have to produce something which also meets this value, right? So you have to show that there is no other cut which takes a value less than 11, right? So this is one possible
Yes.
cut, right? But probably there was some other cut which are with a lesser value. So then you have to really see whether that can happen or not. So okay, so the whole thing is not complete by just producing a cut. Okay, so with this example, what I just wanted to tell you is, yeah, these are like different. This is a kind that even the simple problem had like different solutions, right? And there are different aspects here. Okay, so producing a solution, verifying that it is an optimum, those are some of the things that form an optimization problem. Okay, so those are things you need to learn. Okay, so now coming back, let's try another example. So before that, are there any questions on this question? Is it all clear, like what we were trying to do here?
What is the intuition behind this cut?
What's the intuition
Yeah.
behind?
Huh.
Can you come again? I've not been
Uh,
to hear you.
what's the intuition behind this cut? Is there any intuition?
Behind this particular cut?
Yes, ma'am.
Yeah, so that it's yeah. So actually, if you take any other cut also, you will see that that is an upper bound to the amount of flow you can send. Okay. Now turns out that for this example, this value of 11 is the value of the min cut. Okay. So because of that, you can get that 11 is a solution. So why this was the cut that you chose? Yeah, that really has no answer for that. Okay. It's just that there are multiple cuts, and this one was the one with the minimum value. Okay. Okay. Does it answer your question?
Yes, ma'am.
So yeah. So now just moving on, I just want to show you another example. Okay, so this was an example of a max flow problem, max flow and min cut type of algorithms. So are you guys familiar with max flow? So I want somebody from the undergrad third year class to answer. Have you seen max flow kind of problems beforehand? Anybody can answer. Okay, so you're not familiar with.
See them see these type of problems formally in any of the courses.
You haven't seen.
I remember. Yes, ma'am.
Okay, so yeah, so and that's fine. So I kind of expected that you wouldn't have seen it. So we'll come to this kind of problems later on in the course. This is just to give you a feel of what these kind of problems are. So now I want to come to another problem, which is designing a safe campus. Okay, so in this problem, like there's this network here, and you want to position guards. Okay, so that I mean this the new campus, and suppose there were these 10 locations, and you want to position guards so that all the roads are covered. So if you position a guard at this location, then all these three roads are visible. So let me just bring up another page here. Okay, so suppose this is the same graph that I showed you there. So you have, say, 4 hostels and there's an admin block, and maybe this is, something like CS. Okay, I'm not able to write. Okay, let me just open it again. Oops. Okay, so these are 4 hostels. There's an admin, and maybe these are like the departments. So CS and E wanted to have a road between them, and then there is mechanical and materials. They wanted to have a direct connection, and maybe everything else comes in F. Okay, so if I position a guard here at G, at this node G, then all these roads are visible, A to G, G to I, and G to J. Okay, all these get visible. Okay, so I want to position, I want to be able to cover all the roads in this graph, but I also want to only position minimum number of securities. Okay, so what is the minimum number of securities I need to position at these places? Okay, so any attempt on that? So can you start constructing something? So let me say I'm going to start keeping something at hostel C. So this is one location I'm going to position. Can somebody tell me the next possible location? Any other location which could be a security, where a security can be positioned?
J or H?
G or H. Okay, so
J,
let
J,
me.
J for Joker.
G, is it? Did you see
J for
G or
Joker.
J? J for
J.
Joker. This. J. Okay, this one. So if you put something in I, then there is no use, right? Because it's already covered by C. Okay. And yeah. So now what else could you pick?
A.
Which one?
A for ant.
A for ant. Good. So this one. So is everything covered now? You have this is covered, this is covered, this is covered, BC is covered, this is covered, this is covered, and this is not covered. So this is covered and this is covered. So you still have these nodes, right? There's some more edges which are still, some more roads which are still not covered. So any more vertices? Of course, you need something more to be covered. Some more nodes you need to
Ma'am,
pick.
E.
F.
E only, right? I mean, E or F you can take, but not both, right? So E, if you pick, you get this gets covered. This also gets covered. Now, what else is left?
H.
H.
H you can take. Okay, so and this one also. So are we done?
Yes, ma'am.
Oh
No,
no, what
ma'am.
about this was
No,
okay,
ma'am.
this was about
FI is missing.
FI. FI. This is missing, right? 3, 4, 5. So yeah, FI is missing. So maybe you need to pick one of these. Okay, so let's maybe just pick F. Okay. So I think now everything is covered. So here the number of guards you picked was 6. Okay. So here, yeah. So in this case, it turns out that 6 is the optimal. But how do we know that 6 is indeed the optimal? Okay. So there's really no way to verify that 6 is the optimal other than choosing all possible configurations here. Okay. So in this sense, this problem is actually an NP-hard problem in general. Okay, so yeah, so this is a small instance of the problem, and suppose I gave you a larger road network. Okay, so this is part of network in Bangalore. So if I gave you such a large network, then really it would be very hard to compute this kind of solution here. Okay, so in that sense, what you saw just now is an example of a vertex cover problem. So have you seen the vertex cover problem before?
Yes, ma'am.
Okay, good. You've seen it in some course, right? So yeah, that is what is an NP-hard problem. But the other problem which I made you solve, the max flow problem, that is a polynomial time solvable instance. Okay, so yeah, so that's the point I wanted to make here, that some problems are easy and some problems are hard. When they're hard, you find efficient approximations. Okay, and when they're easy, you find efficient ways to solve them exactly. Okay, so there were some more things I wanted to cover about modeling these problems, but I guess we are kind of running out of time here. So maybe we'll again continue in the next session. Okay, so the next week I will just continue on this introductory session, and then we'll get into some of the preliminaries required for this course in terms of linear algebra and calculus. Okay, so yeah, I guess that's about it for today. Were there any questions, any specific questions you wanted to ask?
Yes, ma'am. Ma'am, like you asked me about that in max flow problem. You asked me how will I know that that is the best solution,
Right.
right? Ma'am, what I thought about it was that what I can do is while doing this backtracking,
Mm-hmm.
if I just change the amount of flow, that is
Mm-hmm.
the inflow and the max flow. Like if a node has an
Mm-hmm.
inflow greater than the max flow,
Mm-hmm.
then uh, or no, if a node has an inflow greater than a max flow, then I can decrease that inflow to a number which is equal to the max flow.
Okay.
And like I can give you an example if you just display the graph.
Sure. Okay, I think I just need to open it again. Give me a second.
Yeah, sure.
Just give me a second. It's just. Okay, why is right not showing here? Okay, let me just show you the graph as it is. Okay. Okay, can you tell me on this one? Because I mean.
Yeah, sure. Like just take the case of node A.
Okay.
So in that case, the inflow is of 10, but the total
Yes.
outflow is of 8.
Yes, right.
So I
4
can
to
decrease the value from H2A to 8.
Okay.
So if I just keep on doing this for all the nodes,
Mm-hmm.
then I will get the optimized solution.
Yeah, but how do you know that this was indeed like what you started off with was indeed optimal, right? Or even in this process, that how do you know that it will converge, and how do you know that it is going to converge to an optimal part? And there's some ordering that you're assuming, right? And
Huh.
right, so
Okay.
right, okay, so there has to be a systematic way. Like probably you have a point there, but it has to be a systematic procedure. Okay, so right,
Okay, ma'am. Thank you, ma'am.
yeah. So okay, any other questions? I think we are kind of running late. Okay, so I guess if not for any questions, we'll stop here, and the next class will be on Tuesday. It's 8:30 class, so let's all start the day with optimization. Okay, so thanks everyone.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.